Hey there, welcome to LSAT Demon Daily. I'm Ben Olson, that's Nathan Fox. We're the founders of lsatdemon.com and our weekly podcast, Thinking LSAT. We have an email here from Drake. Making the argument win.
Hi, Ben and Nathan, or Nate, whichever you prefer. I don't have a preference, actually. I go back and forth. I am brand new to the LSAT as of November, and I think I lucked out in finding you guys before any of the other prep companies! Exclamation points. My question is about sufficient assumption questions. As opposed to some other categories in LR, I hear you guys talk about how I need to make the argument win with the answer choices. But when I get to the answer choices, it's hard for me to parse which answer gets all the way to a win from the ones that don't. Any tips for navigating this? I apologize if this is kind of a silly question. My undergrad classes never demanded this kind of reading. Thanks for your help, Drake.
Yeah, so Drake, first of all, in a sufficient assumption question, you've been given an argument. The argument has a conclusion. It has evidence or premises, or at least one premise. And there is almost always just one reason why the conclusion is not winning right now, why the conclusion has not been proven by that evidence. And you need to have identified that problem before you even read the question. You need to read the argument and be like, oh, yeah, but for X reason, the conclusion isn't proven. And then when you read the question and it turns out to be a sufficient assumption question, you already know the answer. That's not always true for other question types. It's harder to predict the answer in a necessary assumption question, for example. You can predict an answer that might work, but on sufficient assumption questions, it's almost always the case that if you did the analysis correctly while reading the argument, you will know what would make the argument win.
Yep.
And if you don't, you actually want to go back and figure that out before you start reading the answer choices.
Yep. It's more like algebra or computer science than it is like whatever reading classes you had in undergrad. You know, I love my math examples about sufficient assumption questions, or the different, like, necessary and sufficient assumption questions.
Yeah.
I have math examples that are like, just imagine the equation x plus 2 equals 4. How do you make that equation win? X plus 2 equals 4. Okay. If that's the entire argument, x plus 2 equals 4. And then the question says, which one of the following, if assumed, would allow the equation to be correct, or something like that.
Yeah.
Right? You predict that answer.
Already, before you even read that question, you would look at that and you'd say,
Right.
oh, so X is 2? Huh, okay.
Right. You have to be able to just complete it yourself. So how do we get to, like, valid? Right?
Yeah.
So yeah, you see x plus 2 equals 4 and you go, well, x equals 2. And if x does equal 2, then yeah, x plus 2 equals 4. So that's how you know that x plus 2 makes that equation win. Necessary assumptions can be far harder to predict, though, because you could get into the answer choices on a necessary assumption question, and it could be like x doesn't equal 3.
Or x is positive.
X is positive, that's necessary, because if it's not positive, it's not 2. X is even, because if x is not even, it's not 2. X is not negative 3, because if it's negative 3, then it's not 2. So you could go on infinitely with necessary assumptions in that equation. But the sufficient assumption is just, well, it's the answer to the damn question. It's the one that wins.
Yeah.
X equals 2. You can do a similar example using, like, I was thinking about like computer code. You know, imagine a program that was like, there's only one line of code. Output X. Okay? Output X. That's the whole program. And if there was a desired output, which was 2, right? The program says output X, therefore the output will be 2. Well, what's the missing line of code?
X equals 2.
The missing line of code is X equals 2. If you have an additional line of code that establishes X as 2, then X equals 2, output X. Okay, so the output is 2. But it's like, you should be able to fill in that blank of like, well, what did we need to put in here in order to make this equation valid or make this program output what we want it to output?
Yeah, and in that example, right, the answer that would make that work is that X is equal to 2, where sometimes you can see a slightly different answer is maybe the correct answer says something like X equals 3 minus 1.
Yeah, or X equals 1 plus 1, or X equals the square root of 4, or whatever else. They could, like, there's other ways that you could say that.
But it is always going to come back to that point that X equals 2. It's not going to go into some other direction. Yeah.
Right. So 2 tips then for Drake. 1, hopefully you have understood our like definition of what a sufficient assumption is. Sufficient assumption makes the argument win. And you think about it in terms of math or think about it in terms of computer science, where it's like, okay, there's one missing element here. That's the element that has to be added to this argument in order to force its conclusion to be true. Predict that answer. Don't just go into the answer choices. Because, notice what he said. When I get to the answer choices, it's hard for me to parse which answer gets all the way to win from the ones that don't. Well, okay, but you should have predicted what that win condition looks like before you even get to the answer choices.
And just ask yourself, does this answer fulfill that in some way, shape, or form?
But make the prediction first.
Yeah.
Make the prediction first, right? Okay, I need to establish that X equals 2. And then when you get to an answer that says something like X is the cube root of 8, you go, oh shit, well, I wasn't expecting that.
Okay.
But if the cube root of 8 is 2, then yeah, okay, fine. That establishes that X is 2. And that gets there. It's like it says, I needed it to say X equals 2. But if you say X equals 1 plus 1, that's another way of saying X equals 2. And that'll get me there. So,
or all numbers are equal to 2.
Oh, sure. Yeah.
Or all variables are equal to 2. That's overkill, but it works. It gets X to be 2. It just makes so X then you're 2. Good. Yeah.
Everything is 2. All atoms in the universe are now 2. Okay, fine. Great. The next is 2, I guess. That's the type of thing that like the answer could be unbelievably overly strong. And still, as long as it does the thing that has to be there to make the argument win, then that's great. So sufficient assumption questions, I think, are the or tied for the most predictable type of question on the law school admission test. Would you agree?
Sure. Tied with main point questions, probably.
Main point questions. And main point questions and sufficient assumption questions, I think. It's just like, hey, what was the conclusion of that argument? Or, hey, what's the one missing thing that will make this conclusion valid?
Yep.
You always predict those, and then you just don't settle. When you get into the answer choices, you need something that says that same thing, although it can say it in different words. Oh, and we have one we can try.
Yeah, let's do it.
Nice. Test D is additional extra challenging questions that we've started writing for lsatdemon students. They are opt-in only. And we have a Test D question that we can freely discuss here on the podcast because we own it. We wrote it.
All right, I'll read it. If Steve comes into the office on Monday, Karen will show up too.
Okay, so that's conditioned on Steve showing up. If Steve doesn't show up, I don't know anything. It also doesn't work backward. So if Karen shows up, she could be there with or without Steve. The rule really is triggered on Steve. If you see Steve, you got to see Karen. And I guess another way of saying that is if you don't see Karen, you can't see Steve. Because Steve requires Karen.
Yep, on Monday.
Oh, and it only applies on Mondays, yes.
Yep. The passage continues, if Monique comes in on Monday, Paulina will be there as well.
Okay, so this is two of the exact same rule, just using two different players. So
Okay.
Steve and Monique here are parallel.
Mm.
Karen and Paulina are parallel. Everything I said about Steve and Karen applies to Monique and Paulina. And it also is only on Mondays.
Okay. Next sentence. But Karen and Paulina never come into the office on the same day.
Oh, clever. All right. So then you just have to think about it.
Mm.
This is an
Mhm.
excellent question. Good job to whoever on the Demon team wrote this question, because this is exactly representative of the type of shit that's going to appear on the LSAT, where you were given some factual rules and then you're given the opportunity to just think it through.
Yeah.
I would always think it through before we get to the conclusion, right? I don't care what the next sentence says.
You think
I'm
it
gonna
through any time you get new information
yeah,
that relates to previous information. When
yeah,
you read the second sentence, you're like, it's
yeah,
about two different people, so it
yeah.
doesn't really relate to the first sentence, and so you just kind of absorbed it and moved on. Yeah.
That rule about Karen and Polina applies on every day,
Yeah.
which means it
Including
applies on
Monday.
Monday.
Yep.
And so then I can infer that on Monday, I'm never going to see Steve and Monique both on Monday. Because
Yeah,
if
in the
Steve's
office.
there,
Yep.
Karen's there. And if Monique's there, then Paulina's there. But you can't have
Yep.
Karen and Paulina. So that means you can't have Steve and Monique. Now, of course, on other days, you could have Steve and Monique.
Mm-hmm.
But you can't ever have Steve and Monique on Monday, because then that would require Karen and Paulina to be together on Monday. Okay, so I've thought through the facts as far as I can think them through so far. If this turned out to be a must be true question, the correct answer could easily be, if Steve's in the office on Monday, Monique won't be.
Okay.
Okay.
Thus, the office will not have a fun atmosphere on Monday.
Well, I've already learned that you can't have Steve and Monique on Monday.
Mm-hmm.
So, giving you some credit for making sense, right? I mean, the arguments on the LSAT don't necessarily have to like make sense. They sometimes are just bizarre, weird
Yeah.
arguments.
Yep.
But if this argument is going to make sense, I think what you're trying to tell me is we can't have a fun atmosphere if we don't have both Steve and Monique.
Yeah. Or another possibility here is you can't have a fun atmosphere if you don't have Karen and Paulina.
Yeah, although that shortcuts, that's such a, I mean, that's true. That would get you there. But that actually would ignore the first and second sentence. And so it's like that could be the answer. And that is sometimes what the correct answer will do on a sufficient assumption question. Like there can be multiple ways to get to the same conclusion. But it would surprise me. It would make it kind of actually an easier question.
It would, because it wouldn't require you to draw
To
the
under
conclusion from the first three sentences. But I'm just saying, hey, look, any of that would solve this problem.
It would solve the problem. But again, my prediction is if you don't have both Steve and Monique on Monday, you can't have a fun atmosphere. Actually, it doesn't even need to mention Monday. It could just say, if you don't have Steve and Monique, you're not going to have a fun atmosphere.
Yeah. Well, that would be overpowered, but that's fine on a sufficient assumption question.
Yeah, no, never says which one of the following, if true, is narrowly tailored and would allow the argument's conclusion to be properly drawn, right?
Yeah.
That would be
Yeah.
like a hybrid necessary and sufficient question. But they're asking us here, it says, which one of the following, if true, allows the argument's conclusion to be properly drawn? So I just got to make the argument win.
Okay. By the way, I want to say this. These questions, as you said earlier, Nate, are so predictable. And I know for a fact that the correct answer has to address the concept of fun atmosphere.
True.
If it doesn't address that, yeah, then we have a problem here, because I need to prove that idea.
Scanning all five answers do talk about fun atmosphere.
Okay.
But absolutely, if they bring up new shit in the conclusion, then a sufficient assumption question has to address that new shit.
Yep.
Okay. You gonna read the answers to me?
Oh, yeah. My job. Okay. A, Whenever Steve and Monique are both in the office, it has a fun atmosphere.
I'm trying to prove that we're not going to have a fun atmosphere on Monday. And the only thing I know about Monday is that I can't have both, excuse me, I can't have both Karen and Paulina. I also can't have both Steve and Monique. So I want, if I don't have Karen and Paulina, I can't have a fun atmosphere, or I want, if I don't have both Steve and Monique, I can't have a fun atmosphere. That's what I'm looking for.
Yeah, this is going in the wrong direction, right? If you have both, it's going to be fun, but that doesn't mean if you lose one, it's not going to be fun.
Right.
B, the office never has a fun atmosphere when either Paulina or Karen are there.
I have no evidence that Paulina and Karen are going to be there. I don't,
Yeah.
without evidence that they are going to be there. Yeah, I don't see how that proves that I'm not going to have a fun atmosphere. They can both be
Well,
gone, can't they?
they can both be gone. It says both, but Karen and Paulina never come into the office at the same time on the same day. They
I
also
see.
might neither come in, right? Yeah.
So that answer is seeing if you are confusing sufficient for necessary or misunderstanding the rule about Karen and Paulina, right? Karen and
Mhm.
Paulina can't come in on the same day, but that doesn't mean they can't both be gone on the same day.
Mhm.
And if you thought they can't both be gone on the same day, then you think B is a sufficient assumption of this argument, but it's not.
Yeah.
Okay.
C, the office always has a fun atmosphere when Steve and Paulina are there.
Again, I mean, an answer that says the office always does have a fun atmosphere in any circumstances is not going to help me prove that the office is not going to have a fun atmosphere in other circumstances. So no matter what it says after the office always has a fun atmosphere, that's just not going to be the answer. Furthermore, I have no idea whether Steve's going to be there. I have no idea whether Paulina's going to be there. And so, like, that could only be used to prove that there is a fun atmosphere. And I don't even know whether those guys are going to be there. So, how does that do anything for me?
Yeah. Well, I think your first point is the most important one, right? Okay. It tells me when it will always be fun, but that doesn't tell me when it won't be.
Okay.
D, the office has a fun atmosphere only when both Karen and Monique are there.
Karen and Monique, huh? Oh, I see. That's actually not what I predicted. We could have made two more predictions that we didn't make.
Mm-hmm.
But
Mm-hmm.
when you make good predictions, it does help you to recognize other answers that would do the same thing.
Sure.
So the office has a fun atmosphere only when both Karen and Monique are there, means you have to have Karen and Monique, or else you can't have a fun atmosphere. But as soon as I contemplate Karen and Monique, I remember, well, wait a minute, Monique requires Paulina, and Paulina hates Karen.
Mm-hmm.
So if you can only have fun when you have both Karen and Monique, well, that can't happen on a Monday.
Yeah.
Because on a Monday, Monique requires Paulina.
And that's not going to happen.
So there is a parallel answer to that, which would be the office has a fun atmosphere only when both Steve and Paulina are in the office.
Yep.
And that would be sufficient for the same reason, because you can't have Steve and Paulina on Monday. You can't have Karen and Paulina, so you can't have Steve and Paulina, and you also can't have Monique and Karen.
Yep. Okay, sounds pretty good. At this point, we're just dismissing E to make sure we didn't misread D.
Well,
E,
yeah, I mean, at that point, every answer is wrong 80% of the time. But if I have an answer that I think is a sufficient assumption, and I've even had that like aha moment where I'm like, oh shit, that's actually not exactly what I predicted, but it does the same type of thing in the same type of way.
Yep.
Now I revise, like I'm reading E with a 95 or 99% presumption that it's wrong.
Yep. E says the atmosphere in the office is never fun when both Steve and Karen are there.
Yeah, but who said Steve was coming on Monday? Who said Karen was coming on Monday? Yep. I don't have evidence that either of them have to come on Monday, so that can't be used to prove that there's no fun atmosphere on Monday. Answer here's D, because if you had Karen and Monique, Monique would require Paulina. but Polina and Karen can't both be there on the same day. It breaks the rules. So if that's the rule, that you have a fun atmosphere only when both Karen and Monique are there, then that means you just can't have a fun atmosphere on Mondays.
Great.
Cool. Bit of a tricky one, right? Because there are, I guess, 4 different things that we could have predicted.
Yeah.
Right? A rule that says, a fact that says, you need Steve and Monique for fun, but also Steve and Polina for fun, or Monique and Karen for fun, or Karen and Polina for fun. 4 different combos for fun that would prove, according to these facts, that you're not going to have a fun atmosphere on Monday.
Yeah.
Nice. Anything more for Drake?
No, I hope that's helpful. Keep us posted, Drake. Email daily at lsatdemon.com if you'd like to ask us a question or share some LSAT or law school admissions news. Thanks for listening.